Hello everybody. I made this video at 1:50 originally, and when I started watching what I made, I was like, wow, that one's horrible. So, it's 1 o'clock in the morning here. Let's get to it. This is recap video number 1. We're going to do some recap videos just to review kind of all the calculus. You should know that these videos are not going to be comprehensive in the sense that it's not a good sign, in the sense that we'll be doing every single topic, but we'll do a very broad overview of the topic to kind of dust off the old cobwebs. One thing that you should note here is that I don't know what the AP test is going to look like. So we're going to try our best to get you as prepared as we can to what we understand what the AP test is going to be like. I have my definition for local linearity here. Basically, it's like when you have any kind of curve, any kind of function, and you zoom in on a particular point on that curve. Well, when you zoom in, that curve no longer looks like a curve, it looks like a straight line. And when you get that straight line segment, that piece of line, it's going to be a long video. That line is going to be called the tangent line. Or there's a instant slope. So I'll just put instantaneous rate of change. When you zoom in, you can see how much that function is changing by for an instant. So this is also called an instantaneous rate of change. Instantaneous rate of change. Okay. Let's see. So here's an AP question on a function of the tangent line at x equals 7 lines above the curve. What does this tell you about the concavity of f of x near x equals 7? So here's x equals 7. It has concavity. Concavity makes me think of these four curves. And we're putting a tangent line on each of these at any particular point here. It looks like there are two that are above. So these two at the top are above the curve. The two tangent lines are above the curve. And these two here are below. These two tangent lines are below the curve. The commonality for the top ones are CCD, and the commonalities for the bottom ones are CCU. So when it says that the tangent line at x equals 7 lies above the curve, well, above the curve means that we're going to be a concave down function. So at x equals 7, the function, we don't know what it looks like, but has to be something to that effect, where the blue tangent line will be above the curve. So what does this tell you about the concavity? That the function is concave down. Okay, that's our first answer to the first question. And what is with the tangent line at x equals 7? Would it overestimate or underestimate the value of f of 7.01? Now here's f of 7.01 for both curves. If I just extend this a little bit, and let's go and just do this. Let's go and just extend this one. Let's see, can I move these? Can't move this. Oh man. Alright. Alright, well here's what we'll do. If we look at just this one that's here, the tangent line point, so if I draw this line up, this is where the actual curve is. This is where the tangent line approximation would be. So it looks like in this case, we're going to be over. Tangent line is above the actual function. So this is going to overestimate. And you can try it on, the same would be true if we did the other curve as well. So I'll just put a little note here, above and overestimate, and then below and underestimate. Now, one thing that you can think about is, okay, so this is what the tangent line does. What would the secant line do? And the secant line is that line that goes through 2 points on the curve. But again, this is not going to be a comprehensive video, so think about that on your own. Here's our next topic. The limit definition of the derivative. Okay, so the limit definition of the derivative, there's two of them. This first one is equal to f prime of A. The second one is equal to f prime of A. Also make note that if we have the limit as h approaches 0 of f of x plus h minus f of x over h, this would be equal to f prime of x. So these are the limit definitions of the derivative. I just want to quickly show you where one of them comes from. If you were to have some function that looks something like this, where one point was a, and then we had some other arbitrary point called x over here. Well, if you make the secant line between these 2 points, twink, then the slope of the secant line, again, this function's name would be f, would be f of x minus f of a over x minus a. Because the coordinates here are x comma f of x and a comma f of a. So we get the slope of the secant line here. To make this a tangent line at x equals a, what we do is we move x closer and closer and closer to a. And when we do that, and again, a is frozen here where x is only moving, this y value starts getting closer and closer and closer to the y value at x equals a, and these secant lines start becoming more and more like the tangent line. And the math notation way of doing that is by putting a limit in front, and we say as x gets closer and closer to a, or when you take the limit of the secant line, of the slope of the secant line, you get the tangent line. So that's where these definitions come from to get an instantaneous rate of change. The main idea here again is the secant line. So the secant line is becoming the tangent line. It's supposed to be purple. Tangent line at x equals a. More generally, to find f prime of x, we can use things like product rule, quotient rule, chain rule. I'm trying to remember if these go over it in the next part. Yeah, more generally, find f prime of x. So the limit problems are very specific. I'll show you how to do the AP question in just a minute. To find f prime of x, though, you could also do some other ones. Nope, never mind, that's over there. We'll skip this part. We'll come back to it in a second. Here's an AP question on the limit as h approaches 0 for this difference quotient here, natural log of 4 plus h minus natural log of 4 over h. There's two ways you could do it. Step one, you could do L'Hopital's rule. The reason I know you could do that is if you plug in 0 for h, you end up getting 0 over 0, which means L'Hopital's rule applies. If you try that, then you get the limit as h approaches 0. You're pretending x is h. H is x. So the derivative of natural log is going to be 1 over the argument, 4 plus h, times the derivative of the argument, which is 1, minus 0, because the natural log of 4 is just a number, and the derivative of a number is 0. And at the bottom, we just have a derivative of h is just 1 again. Then if we plug in 0 for h, we end up getting 1 over 4. So that's one way of doing the L'Hopital's rule. One way of solving the limit problem. L'Hopital's rule would definitely save you. A different way, which pertains to what the limit definition above is requiring, is we could find f of x from this function. F of x looks like it's going to be the natural log. Because it's a difference quotient, it has that form of f of x plus h minus f of x. So because this is a difference quotient problem, what we can do is we can find the derivative, since this is what we know the difference quotient is. Derivative ln of x is 1 over 4. And because we know that the x value that they're plugging in is 4, then we could just plug in f prime of 4. So f prime of 4 is equal to 1 over 4. And I made a mistake here. I'm sure you probably caught it. I meant to say this was 1 over x. I was just writing 4 down with anticipation knowing that would be the answer. So there's two ways of getting the of gain, the derivative here. This would be the difference quotient away. So let's go back up and type how we would get find f prime of x. To find f prime of x, and we'll type because goodness knows my handwriting could use some work. To find f prime of x, I'll move that in a second. And establish the function, establish what f of x is. 2, take derivative with whatever rules you know. 3, evaluate with whatever the x value is. Then that's it. Just move this out of the way, and then we'll move on to the next part of how to write an equation of tangent line. Okay, how do you write the equation of tangent line? Well, if you were given a point like a comma f of a, and you were given a slope like f prime of a, then the equation of tangent line would be y minus f of a equals f prime of a parentheses x minus a. Okay, you need a slope and you need a point to write the equation of a tangent line. Ways to find the derivative. One way to find the derivative could be a product rule, a power rule. That's the derivative. Well, I'll leave it at that. I think you know what the power rule is. We could also do the product rule. We could do the quotient rule, which is low d high, low d high minus high d low over low squared HDL. Not HDL cholesterol. We could do the chain rule. And then there's a whole bunch of other formulas like the trig derivatives as well, which you have in your notes. To write the equation of the tangent line to f of x, let's go and do that. So let's get f prime of 2, and this would be a good place for you to pause the video and get an answer. So go ahead and pause the video now, please. Thank you. Hopefully you got this answer. Y minus 4 equals 10 parentheses x minus 2. All the work is there, so again, please pause the video if you're not sure how we got that. Okay, last one is going to be this problem. It's FRQ, so let's go and do it. It says, let f be the function defined by f of x. Actually, you should probably take a minute to pause and see how to do the problem, read the problem first. Question A says, find the slope of the tangent line to the graph of f. So tangent means I need a derivative, so let's do a derivative. The derivative of the function that we're looking for is right here. And it's going to be a chain rule because of that argument. Derivative cosine is negative sine, so negative sine of 2x and then times 2. So I'm just going to make this a negative 2 sine x, 2 sine 2x. Plus, and the derivative e is the function itself times the derivative of the exponent, which is cosine x. Nope. Okay, if we plug in pi, we get f prime of pi is equal to negative 2 sine of 2 pi, which I believe is 0, plus e to the sine pi times cosine of pi. And again, sine of 2 pi is 0, e to the sine pi is 0, so that's a 0, e to the 0 is 1, and we have a cosine of pi, which is a negative 1, so this is going to be negative 1. Okay, and we also need f of pi to actually get a y value, because they only gave me the x value. I needed a y value and a slope, and f of pi is going to be equal to cosine of 2 pi. I'll write this all out for you, plus e to the sine pi. This value is going to be 1, this value is going to be 1, and we get 2. So my equation, I'm going to get y is y plus 1 equals 2. I'm sorry, that's not correct. Y minus 2, because it's going to be the y value. I got those backwards. Y minus 2 equals, this is going to be negative 1, parentheses, x minus pi. X minus pi. Okay. Here's our first answer. Let's go on to the next one. Okay, now we need to find a derivative. Notice that this is a big time chain rule problem because we have a function inside a function. So let's go ahead and just take a derivative first to set ourselves up. I'm not going to do anything with any of the other information. We're just going to get through this problem. The chain rule means you take the derivative of the outside function, keep the inside, and then multiply that times the derivative of the inside. So that's the derivative. Now let's go and plug in pi. So k prime of pi is equal to h prime of f of pi, which I believe we have on the other page, times f prime of pi. So let's see what f of pi was. F of pi was 2. So now we need h prime of 2 times f prime of pi. F prime of pi was negative 1. So whatever this value is going to be a negative value. Alright, now for h prime of 2, h prime, here's the graph of h. H prime is the slope. So I need the slope of this line. Looks like it goes down 1 and over 3. So this is a negative 1 over 3 times negative 1, which is 1 over 3. And that's my answer. For C, looks like I'm going to need a product rule here because I have a function times a function. I'm also going to need a chain rule because of the function inside a function. To do the product rule, I'll choose g to be f and h to be the second function, and I'll set up my product rule here. So m prime of x is going to be equal to, let's do first here, times second prime plus second times first prime. Alright, the first function is g of negative 2x times the second function prime is h prime of x plus the second function is h of x times, we have g prime of negative 2x times negative 2. G prime of negative 2x. Okay. Again, that negative 2, I just want to highlight that part, is from the chain rule of the derivative of the inside. Okay, next, let's go and do plug in 2. So now we have m prime of 2 is equal to g of negative 2 times 2 is negative 4 times h prime of, we're plugging in 2, plus h of 2 times negative 2 times g prime of negative 2 times 2 is negative 4. Alright, let's see what we get here. So now we're going to get g of negative 4 is 5 times h prime of 2. H prime of 2, I think we had on the other page, didn't we? Yeah, h prime of 2 is 1/3. So times 1 over 3. Now we have a plus h of 2, which I don't know if we ever got. So let's do h of 2 right now. To do h of 2, the graph of h is here. Here's h of 2. I remember that we went down 1 and over 3 for, so we went down 1 and over 3. So if we just go over 2 of them, so for every, let me back up here, so for every 1 we go down, and maybe you already have the answer, and I'll just speed this up. So for every 1 we go down 1/3, which means for this part we go down 2/3. So 5 times 1/3 plus 2/3 times negative 2 times g prime of negative 4. G prime of negative 4 is going to be negative 1. Okay, so let's see what we get here. We get 5 over 3 plus 4 over 3, because 2 times 2 is 4. Both of them are negative, so we got positive. That's 9 over 3, which is 3. And then D, so I kind of have already prepared myself here. The question is there a number C in the closed interval such that G prime of C equals negative 4? So this is a mean value theorem question. The reason I know it's a mean value theorem question is because it has that G prime of C equals negative 4. I'll try to add the MVT here. And let's put this in a different color. So the mean value theorem states slope of the secant line I abbreviated this part here. The slope of the secant line is equal to the slope of the tangent line because but basically it's saying equals this IVT doesn't apply here. I don't know if some people tried that or if you want to try that, but it does say G prime C equals negative 4. And if I could look from negative 5 to negative 3 and see these slope values, so on a separate graph of the x values of negative 5 to negative 3, I see that I have a negative 3 slope, and then at negative 3 I have a 4 slope, negative 3 and 4. The reason this doesn't work for an IVT problem is because I want a negative 4 value. My negative 4 is down here. I'm only given these 2 points. I don't really know what happens outside of these 2 points. So IVT fails here is the point of what I'm writing. So how do you solve the problem? You solve it with MVT. And the first thing you need is G of 5 minus G of negative 5 minus G of negative 3, because you need the average rate of change between negative 5 and negative 3. And G of negative 5 is 10 minus G of negative 3 is 2. And we're dividing by negative 2. And oh my gosh, 10 minus 2 is 8. 8 divided by negative 2 is negative 4. And hey, that's what we were supposed to get. So that's great. Now to justify your answer, well, that's the lengthy part. And we have to say, because differentiability, notice we have to mention differentiability because the MVT is not applicable if the function is not differentiable. And if the function is not differentiable, it does say that the function is differentiable right here. So because differentiability implies continuity, because we need continuity and differentiability, then the function is continuous on the closed interval, negative 5 to negative 3, and differentiable on negative 5 to negative 3. Then by the MVT, there is the G prime of C definitely equals negative 4 for some C on that closed interval. And that's your answer, guys. Hope this helped. Thanks for watching. I think this video was way better than the first one I made.